Okay, so I think let me start. As usual, before starting the class, uh, I would like to give you some tips, right? So, tip of the day, if you are very much interested in machine learning business, hope some of you are interested. Have you heard of this? Kaggle. Go to kaggle.com. Look at these courses here. These are very basic courses for a couple of hours, so maybe 18, 20 hours or something like that. You do these courses, online courses, and then participate in these competitions. So you can see that how much prize is there for each competition, and different problems are given. Competition, money is there, of course, because you are interested in money, and some challenging projects, so you can participate. Kaggle, it's a parent company is Google actually. So, earlier somebody started Kaggle, now Google has acquired it. Okay, so it's pretty good thing for machine learning business. If you are very much interested in building machine learning concepts, this course set is so easy that any person even in high school can understand it. Okay, 10th. So you are in first year. So I hope you will be able to do it right and participate. Even if you don't understand a lot of algorithms, but at least you get hands-on, learning, because you see all the things. And Kaggle has a lot of great data set, so very good data set, so that you can write machine learning algorithms and try to build something. Okay, so for machine learning people, machine learning AI people, this is Kaggle. Okay, so now I think I have to finish first module today. So I'm going to give you an idea of RSA crypto system. Before RSA crypto system, I need to talk about Forma's little theorem. Before Forma's little theorem, I have to talk about few basic number theoretic concepts. Using them, we can actually build Forma's little theorem, and using that, I can give you an idea about RSA crypto system. So the last exercise that is given in your tutorial 1 is about implementing it. You can easily write a program to implement it, right? It's a very good one. So maybe, so maybe by next week or something, you can do that. It's a great learning. Okay. So also I will talk about briefly couple of ciphers. I'll give you some history about ciphers, and then I'll talk about Caesar cipher, especially, or substitution cipher, how it works. It's very easy. So simple application of modular arithmetic that we saw, modular arithmetic, integer modulo n, that we are doing it. So basically, I am going to now talk about the application of these concepts in our daily lives. That's all. Okay. So let me start. Sure that. Okay. So I think in the last class, we talked about this result. If GCD of A and N is 1, then the equation AX congruent to B mod N has a unique solution. In other words, what it says that if GCD of A and N is 1, that means there exists inverse of A in the system, right? A into X, if actually B is 1, of course, in that case, there will be inverse, right? If B is 1, right? So let me use this fact. to prove something really interesting thing. I'm going to prove this result which I gave you earlier for a t time. Zn is a field if and only if n is a prime number. I hope some of you might have proved it, but anyway, if you have not done it, we can do it here now. Open square means proof starts. Suppose n is a prime. So we are assuming this side of the theorem. We assume that n is a prime number. Suppose n is a prime. Now I will show that Zn is a field. Of course, all other operations are easy to verify. Only one thing is left, which is the inverse. So we are going to talk about inverse. Now choose a non-zero element in integer modulo n. Okay. Now since n is a prime number, GCD of a and n is 1. Right? Because n is a prime number, so GCD of a and n, any number a. So I mean, since a belongs to 1, 2, 3, and minus 1. Okay. Now, since GCD of a and n is 1, there exists an integer x such that ax is congruent to 1. Okay. Therefore, every non-zero element a has an inverse. Inverse means because the product of a and x is 1, right? So x is the inverse of a. So Zn is a field. Now, to prove the other part, that I'll assume that Zn is a field, show that n is a prime number, right? That part is left. So I've shown you that if n is a prime number, then Zn is a field. Now I'll take contrapositive statement, means I'll assume that suppose n is not a prime. Suppose n is not a prime. If I can show that Zn is not a field, we are done. Okay. If n is not a prime, then n is a product of two numbers a and b. N is a composite number where a and b are greater than 1, of course, product of two numbers if it is not a prime, right? Composite numbers. But this implies that n is equal to ab is equal to 0 in integer modulo n, because everything is modulo n. So that means there are two numbers a and b not equal to 0 such that their product is 0. That means there exist 0 divisors. Zn is not a field, right? Simple. Zn is not a field. That is closed. So proof is done. Now, I will give you one example. I am now ready to prove Fermat's little theorem. Now, in order to prove Fermat's little theorem, yes. Yes. Suppose n is not a prime number, it's composite number. That means n is a product of two numbers a and b which are greater than 1, right? So both are non-zero. So that means n is equal to AB, but n is 0 modulo n. So A into B is equal to 0. None of them is 0, so it is not a field. Now, if you want to be a good engineer or if you want to be a good mathematician, you should have one property, right? And the property is शून्य में देखना, right? Observe. Do you observe something here? Let us take a prime. And let us take a set. Okay. Now, I multiply, I consider this set I into 2 mod 5, I is equal to 1 to 4. So I started with a set 1, 2, 3, 4, and there is a given prime p is equal to 5. Now I consider the set. Every element of the set I multiply with 2. 2 is a fixed number. I can take any number a. Right now I'm just multiplying it with 2. What do you think you will get here? Modulo 5. Let us write it down. We will get 2, 4, 1, 3. Right? So essentially what is happening? We started with a set 1, 2, 3, 4, and there is a permutation of the numbers, right? Permutation. In fact, this property holds in general. If you take numbers from 1 to n, right? Take a fixed number a, non-zero, multiply with every element, modulo n, you get a permutation. So I can write it down as a lemma. Yes. Not audible. Okay. Take another example. Suppose p is equal to 7. And consider this set. What you will get? 2, 4, 6, 1, 3, 5. Very good. So that means a permutation. So what I'm saying that if you take a number, a set of numbers, okay, 1 to n, and multiply with a non-zero element a, everything, and reduce it to modulo n, you get a permutation of the numbers. Some permutation. So here 1, 2, 3, 4 became 2, 4, 1, 3. Here 1, 2, 3, 4, 5, 6 became 2, 4, 6, 1, 5. Got it? Just permutation. So actually mathematicians do these things just by observing. Do some examples, observe it, then try to make it as a lemma and then prove it. That is how you discover mathematics, right? Okay. They don't, I mean, nobody discover mathematics like, okay, let us start with a theorem. Then you have to first play with the numbers, observe the pattern. Observation is very, very important. You know, observing the pattern in a data. Okay. Okay. So I am writing it as a lemma. P is a prime number. For a fixed non-zero A in ZP, consider the set I dot A mod P. Then this is a permutation of the set 1, 2, 3 up to P minus 1. Right? Whatever we observed, I have written as a statement, right? Fine. P is a prime number for a fixed non-zero element A in ZP. Multiply everything in the set by A. and reduce it to modulo p, then you get a permutation of the numbers 1, 2, 3 up to p minus 1. Some permutation, right? Now the machinery is ready to give you the proof of Fermat's little theorem. You know about Fermat's little theorem, Fermat's last theorem? Any idea? अभी सुना था Fermat's last theorem, Fermat's little theorem? These are some famous theorems. Fermat's little theorem is simple to prove. Fermat's last theorem is someone who proved it, Andrew Wise. He started working on the proof from the age of maybe 13, 14, and he proved it when he was 42 or something like that. Okay, so this much time he took to prove Fermat's last theorem. And the Fermat last theorem says that x raised to power n plus y raised to power n. So x raised to power n plus y raised to power n is equal to z raised to power n. This equation, when n greater than 2, has no solution other than the trivial solution. Very simple. Fermat's last theorem. And Fermat has written on a corner of a register, I have found a proof, but the space is very little or something. So I have, and then people started proving it and they could not prove it. So many mathematicians, because of Fermat's last theorem, a lot of advancement happened in mathematics. And finally, it was proved by Andrew Wise, which was pretty big result. I mean, when something is unsolved for a long time, people, later on, he actually got a prize, of course. So that is it. So let us give you an idea of Fermat's little theorem. P is a prime number. A raised to power p minus 1 mod p is equal to 1 in ZP. For each non-zero A in actually अभी तक आपने जो बिजनेस किया है फाइनाइट फील्ड के साथ GF4, GF8 and so on, you will see that similar property holds there also with the elements. Okay, each element satisfies a certain equation. Okay. Anyway, so which is the same thing here. So A raised to power p minus 1 mod p is 1 in ZP for each non-zero A in ZP. We take any non-zero element in ZP, integer modulo p, raise it to power p minus 1, reduce it to modulo p, you will get 1. Beautiful theorem, right? And so we can try to prove it. Look at this set. Proof. Look at this set. 1 into A, 2 into A, 3 into A, dot 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 p minus 1 into A, mod p. A is your non-zero element, right? So this will be what? A permutation of the numbers 1 to p minus 1. So this will be nothing but 1 into 2 into 3 up to p minus 1 mod p. Okay. Now, this is a product. So that means 1 into 2 into 3 up to p minus 1 is what? Factorial p minus 1. Right? And this A is p minus 1 times. So factorial p minus 1 into A raised to power p minus 1. This quantity is equal to factorial p minus 1 product. Right? So factorial p minus 1 into A raised to power p minus 1 is equal to factorial p minus 1 mod p. Now, since every element 1, 2, 3, 4 up to p minus 1, right? Each of these elements has inverses. I can cancel them 1, 1, 2, 2, 3, 3 every both sides, and we are left with a raised to power p minus 1 is congruent to 1 mod p. Simple result, right? Result आया कहाँ से? Because of this fact, right? This is the interesting observation, right? We use this fact here that this is nothing but permutation of 1 to p minus 1, that's all. So that means when we consider product, it will remain same, right? So that means factorial p minus 1 times a raised to power p minus 1 is congruent to factorial p minus 1 times mod p. Essentially, factorial p minus 1 we can cancel on both sides. So we are left with a raised to power p minus 1 is congruent to 1. And we have got the Fermat's little theorem. So very useful result. And I think there are some examples I have given you in the tutorial 1 to compute, right? So you have to basically use Fermat's little theorem, compute those things, right? Okay. Now, yes. Yeah, I mean, you can assume it. I just write it only once. So whole expression is mod p, no problem. The left hand side, right hand side, both sides it is there. No, I mean, we know that what is happening, right? The thing is reduced to modulo p on both sides. That's not an issue. Now, another very interesting thing I am going to talk about is Chinese Riemann theorem. Made in China, right? So I'm not going to prove it. I will just mention the result, and then we are going to use it in the RSA crypto system. सब कुछ तो नहीं पढ़ा सकते ना, हमको मूल तत्वों पर विचार रखना चाहिए, राइट? शास्त्र अनंत है, so we should focus on. Before going this, I just want to ask you, how do you solve this equation? 3x congruent to 4 mod 7. Solve for x. शायद आईआईटी जेई में इस तरह की प्रॉब्लम्स करी होंगी कुछ, राइट? आप कौन सी कोचिंग करिए उस पर डिपेंड करता है. I think the best coaching is Fit JE, right? Because the questions are good, right? What, 6? Asha, so answer is okay. So what we can do, we can multiply both sides by 3 inverse. So x is equal to, now what is 3 inverse? 5. So I hope now you understand how to solve these equations by now. Yes. 3 inverse, this is 1. So x is equal to 4 into 3 inverse is 5, modulo 7, right? So x is equal to 6. So this is easy equation. Only single equation is given. But what if there are multiple equations given? And I ask you a solution of x which satisfy all k equations, say. I'm going to consider something like this. Now there are 3 equations given. You have to solve for x. How do you solve? I think you can solve it on using a cup of tea, right? So just sit down in the evening and then you know how to manipulate. But anyway, I am going to give you a general formula without any proof. First equation, x is congruent to a1 mod m1. Second equation, x is congruent to a2 mod m2, and so on. Last equation, an mod mn. There are n equations. How do we solve? So what we do actually, we take the product of these mi's, m1, m2, m3, mn, right? And of course, this condition is given there that GCD of mi and mj is 1. So this has a unique solution, modulo m1, m2, mn. So if m is equal to m1, m2, mn, the product of all, I can write down mk as m divided by that particular k, mk, small mk. Small m is product of all m1, m2, mn. You divide it by mk, whatever is the kth equation. So that we call, I am calling that number as capital Mk. Then GCD of mk and capital Mk will be 1. Because it will not be there anyway, right? So now this means there exist integers yk such that mk times yk is equal to 1 mod mk. That means therefore yk is nothing but inverse of capital Mk. And the solution is x is equal to a1 m1 y1 plus a2 m2 y2 mod m, where m is product of all mi's. Now, rather than proving this, I would like to say that you can verify this. For any equation, say mk, kth equation is what? X is congruent to ak mod mk, right? That is our kth equation. So reduce everything with mod mk, what will happen? Reduce everything with mod mk. You will left with one expression because everywhere there will be mk other than one place, right? When you reduce it mod mk, you are going to get x is congruent to ak mod mk, okay? Now mk into yk is 1. So x is congruent to ak. So this equation is actually satisfying the kth equation. I mean, like that you can verify first equation, second equation, third equation, and so on. This value of x satisfies all the equations. Some calculations, nothing more than that. There is no high-fi mathematics here. It's only high school mathematics, right? From where you are doing high school, that matters a lot. Okay, now the most beautiful celebrated result, RSA crypto system, right? So this much is enough. In order to show you what is, first I will tell you, yes, what is RSA crypto system, and then I will use the concept of Fermat's little theorem and Chinese remainder theorem to prove that it works. Then you have to just implement. That's all. I am giving you only implementation task, which is easy, right? Algorithm तो पता हो गया. Program लिखना तो बाएं हाथ का खेल है, 7 दिन का है, right? Any syntax you can learn in 7 days if you have read Art of Computer Programming, right? Okay, as I mentioned in the last class, Lewis, Shamir, and Edelman, three mathematicians, proposed this thing based on the idea of have a Hellman key exchange problem, which was given in 1976, and this crypto system was proposed in 1977. Okay, and immediately they form a company and they made a lot of money. So if you know mathematics, you can earn a lot of money, right? Simple mathematics. So, okay, so let me give you some idea. So we assume that, normally they assume there is Alice and Bob. All these American people, if you want, you can assume Ram and Shyam, right? So that's up to you, okay? So there are two people who are exchanging the messages, right? So what is Bob's algorithm? First, choose large prime numbers, P and Q. Now you have to watch it carefully. Slowly, carefully, observe its beauty. Observe the beauty of this, okay? So, choose large prime numbers, P and Q. P and Q are large prime numbers, fine. Compute n is equal to P into Q. So Bob is doing all these things. Choose two large prime numbers, P and Q. Compute the product, n is equal to P into Q. Now third, choose a number E not equal to 1. This is known as exponent actually, such that GCD of E and P minus 1 into Q minus 1 is 1. Choose a number E. Bob is choosing a number E such that GCD of E and P minus 1 into Q minus 1 is 1. Okay? ये क्यों आया, ये क्यों करना पड़ा, ये सब है, इसके पीछे कहानी है, बट पहले तो समझ लेते हैं ना what is this. So, choose two large prime numbers P and Q. Compute this product, n is equal to P into Q. Choose E, which is not equal to 1, such that GCD of E and E minus 1 into Q minus 1 is 1. And that means, now what you do, fourth, compute D is equal to inverse of E mod E minus 1 into Q minus 1. Mod P minus 1 into Q minus 1. Inverse exist karega, nahi karega, and all those things. I'm not worrying about it anything right now. I'm just showing you the flow. Okay. D is the inverse of E modulo this quantity. Okay. Fine. Now fifth, publish E and N. These are known as public key. These two numbers, E and N, are public key. Means it is available in some directory or something. Okay. Keep D secret, private key. So this is the whole preparation. There is a public key and there are two private keys, E and N, these two numbers. Got it? ध्यान से देख लो 1 मिनट के लिए, so that we go into the next step. दो large prime numbers लिए, product लिया, N बनाया, right? And choose E which is not equal to 1 such that GCD of E comma P minus 1 Q minus 1 is 1. E is working as our public key. Pair of public key means one of the key. Compute D which is inverse of E modulo P minus 1 into Q minus 1. Okay. Keep D. So this D is secret. Okay. D को अपने पास रख लिया. Fine. Now what? Now, Bob's public key is available to everyone. So E and N is known to anyone. Now what Alice is going to do? Alice is sending message X Bob. So if Alice has to send this message, what she need to do? She wants to send a message X to Bob. She knows E comma N. Okay, E comma N is known to anyone, right? The first thing, she will read the public keys. And N. सबसे पहले तो पब्लिक की पढ़ लिया, सबको मालूम है, मैंने भी देख लिया, right? Note it down what is E and N. Second, compute X raised to power E. Not N. Call it Y. जो हमारा मैसेज था उसको पावर E कर दिया. E is what? Public key. And reduce it to modulo N. N also we know. Y is equal to X raised to power E mod N. X is a message. X is a message which Alice wants to send to Bob. Okay, so from that message, so she raised it to power E, which was one of the part of public key of Bob's, right? Third, send Y to Bob. So rather than sending a plain text X to Bob, she is sending X raised to power E. X raised to power E to Bob. Okay. Now what Bob does? Bob receives Y from Alice and compute Y raised to power D. Remember D was what? Private key of Bob, right? Now he's going to raise whatever is received from Alice raised to the power secret key D. And of course, mod N. Read Z. So this works if we show that Z is equal to X. Right? If we are able to show that Z is equal to X, we are done. Got it? Alice wants to send X. She raises it to the power E. E is the public key of Bob. Send it to Bob. Call it Y. So Bob will raise it with his private key. Compute this mod N. If this Z should turns out to be equal to X, then our system is working. This is the beauty. Now you see that it is actually working. Somebody can think of these kind of things in 70s is a great thing. By the way, Edelman invented after that DNA computing. So he is working in biology. So proof. So Z is equal to, okay, so now be careful. Z is equal to Y raised to power D. Y was received from Alice, raise it to the power D. D was private key. That is over Z. I show you now that this Z is equal to X. How? Now Y is nothing but X raised to power E mod D. You remember? X raised to power E was Y. Now since GCD of E and P minus 1 is 1, this implies that, and actually E and D are inverses of each other, you remember? go back and you can see that I have written this here. D and E are inverses. So D into E is equal to 1, right? So ED is equal to this. This implies that EZ is equal to 1 plus some k times P minus 1 into Q minus 1. Remember P and Q are prime numbers, right? Then what? So y raised to power D will be what? X raised to power ED, right? From here is equal to X raised to power 1 plus k times P minus 1 into Q minus 1, right? Is equal to X times X raised to power k times P minus 1 into Q minus 1 mod n, right? हमने खाली x को अलग कर लिया, right? X into x raised to power k times p minus 1 q minus 1. Now I am going to look at this quantity. I will show that if this quantity is 1, our job is done, right? If this quantity is 1, is equal to x. So what we do now, we are going to take help of Fermat's little theorem. Assume that GCD of x and p is 1. This implies that x raised to power p minus 1 congruent to 1 mod p, where p is a prime, right? By Fermat's little theorem. And similarly, GCD of x and q is 1 will imply that x raised to power q minus 1 is congruent to 1 mod p, right? This implies that y raised to power d will be x times x raised to power p minus 1 k times q minus 1 congruent to x into 1 mod p. Agree? Because x raised to power p minus, I have to show that it is with respect to modulo n. I am now showing it with respect to modulo p. With respect to modulo p, there is no problem because p is a prime number. I am applying Fermat's little theorem, right? So x into x raised to power p minus 1 raised to power k times q minus 1. I can write it like this. This quantity is 1. So the whole thing is x into 1 mod p. Similarly, you can show that. So I have shown that this is x into 1 mod p. Similarly, we can show that y raised to power d is x times x raised to power q minus 1 k times p minus 1 congruent to x into 1 mod q. Again, Fermat's little theorem on q. When we apply on q, the same thing is this. So y raised to power d, that means we got y raised to power d is congruent to x mod p, and y raised to power d is congruent to x mod q, where p and q are prime numbers. Now I can apply Chinese remainder theorem. P into q is n. So this whole thing will be true. X mod implies that y raised to d, and our job is this is your z, right? So this is the beauty, right? Applying the Fermat's little theorem and Chinese remainder theorem to arrive at the result. Okay. Now your job is to implement it. That is your last problem in the tutorial 1. You have to implement it. I think last year, many times students have implemented it. They enjoyed it. So you can send messages, display public key and see. Many times people could not understand what is happening in mathematics, but when they implement it, yeah, it is coming. So they enjoy, right? So you need to see that. So now I think अभी तो थोड़ा टाइम है ना 5 मिनट. Now I am not going to write anything, but I will show you some pictures. So since we are talking about cryptography, uh, one question that I always ask, any mathematics, where is it started? Of course, in India, right? Cryptography started in India. No, so there are many, I mean, this is pretty beautiful, interesting thing. By the way, what is cryptography? Study of building secure crypto system, like RSA crypto system is one of them. Cryptanalysis word is study of breaking crypto systems. How do you break a crypto system? The first book that was written by anyone about this was Chanakya, you know, विष्णुगुप्त. धनानंद के बाद जो आया था ना, चंद्रगुप्त मौर्य के टाइम पे, राइट? सो चाणक्य. So he wrote the first book of breaking crypto systems. Okay. Cryptology is study of both cryptography and cryptanalysis. Okay. Normally, cryptanalysis is difficult task. Analysis करनी पड़ती है, right? When you are breaking a system, but it's beautiful anyway. So secret talking started in Mahabharata. So I hope you will not be able to understand what is written here, by the way. But there are a lot of written documents in India which were found. One of the famous one is Kam Sutra. So where they talked about Malicha Vikalp. Malicha Vikalp was something that you need to learn. Everybody has to learn. Okay. And that crypto system actually, they assume random pairs. Of course, it is given in Hindi alphabets. I have written here in English so that you understand what does that mean. You take random, so all alphabet A to Z, take random pairs and replace. So Q with M, P with U, I with S, and so on. Just take random, okay, random pairs, and then you use them. So basically, if you are basically writing, I will kill you. So I will be what? S. And W will be what? D. Then I will be SS. Right? No, sorry. I S and L means KK. So like that. You just substitute the alphabets according to these random pairs. Okay. This was very common in India. Long time ago, before what we study. There is also in Indus Valley civilization nearby Gujarat. There's a lot of work also available in this Jayamangla commentary, Quatillium cipher. Okay, this cipher, spoken secret. So will visit you tonight means this will visit, this visit, this you, this tonight. This kind of things. Spoken secret, you know. Early cryptanalysis by Chanakya. You can study about these things. This book is interesting. Modern cryptography started a bit late, but especially at the time of world wars, you know, a lot of work has been done on cryptography. You can see, we can briefly talk about Caesar cipher. You can see that a lot of work is done. In a lot of work was also done in Middle East, you know, clay table. You see ciphertext, how this kind of rod is used and they wrap it around by writing the things. An adverse cipher, specific kind of substitution cipher. Caesar cipher I'm going to talk about briefly. This is Al-Khindi. He has written a lot of books on cryptanalysis, but this is far late than Chanakya. By the way, this is something very beautiful, right? This is the modern cryptography. We can say that these things evolved into what you use every day, ASCII codes, right? So it evolved from here. This was the origin. Omnia per omnia, bilateral cipher. Can you observe anything interesting here? Anyone? Every letter is binary. So A is A, B is A, B, and so on. That is fine. Anything else? No, that is fine. I mean, everything is binary anyway. That is not very interesting. No, that is fine. That is how you write artistic English, right? This is at the time of Shakespeare. Advancement of Learning. I took this picture from the book Advancement of Learning by Francis Bacon. You observe at the time of Shakespeare, 1605. This is 1605. What was the size of English alphabet? It was not 26. Observe which one is missing. J is missing and U is missing. How will you write Jesus without J? Or you see, it's very interesting thing, right? English, this is the standard of English, right? You see, county, court, spelling is C-O-V-R-T. House is H-O-V-S-E. H-O-V-S-E, this is the house. Okay. This is English, you might have seen, right? You are expert in English. So anyway, cryptography is divided into two parts. Symmetric key cryptography, like ciphers, which I am going to talk about only one example. Asymmetric cryptography like RSA, DSA, Elmer, Irpiker. This is used in your smart card. Okay. These are stream ciphers and these are block ciphers, DES, 3DS, blue. AES is used currently. This is broken later recently. So now AES is used from 2001, Advanced Encryption Standard. Anyway, so where is your startup? So many startups in cryptography. You see. So this is a nice. Every time you will find something like this from me, that where is your future? You can start a company in cryptography easily. In India, there are very few. Right? So this is a nice area. You full of mathematics and fun. Build a crypto system or build a security tools and everything. And so many cryptography companies are there making a lot of money. Okay. So especially in blockchain and cryptography, a lot of work is there. Anyway, so that's all for today. I think next class I will talk briefly about the Caesar cipher, though it's very simple. But I think you have done in assignment 1, right? No? Fine. We will do it briefly and then we'll move towards what is known as logic. So next chapter will be logic. Thanks.